Good morning, distinguished guests, respected colleagues, and dear participants. It gives me immense pleasure to welcome you all to the inaugural session of this faculty development program on the application of technology for environmental sustainability. I, Dr. Sumita Daya, and for me, it is an honor to stand before such a diverse and dedicated group of academicians and professionals who share a collective passion for advancing knowledge and contributing to a sustainable future. Before moving ahead, I would like to call Dr. Anurag Gaur to welcome and present a memento to the Honorable Vice Chancellor of NSUT. I would also like to call Dr. Vinod Kumar to welcome and present a memento to Professor Shigeru Yamashita. Now I would like to call Dr. Amit Sengar to welcome and honor our counterpart in IITR, Dr. Ashok Kumar. Thank you. To mark the beginning of this event, we would like to perform the traditional lamp lighting ceremony, which symbolizes the dispelling of darkness and the illumination of knowledge and wisdom. It is our honor to invite our esteemed dignitaries to join us for this ceremony. Thank you for lighting the lamp and marking the beginning of our event with such grace and positivity. We are now ready to proceed with our program. The theme we are exploring over the course of this program is not just timely, but also crucially important. Today, as we witness the rapid depletion of natural resources, the alarming rise in global temperatures, and the significant loss of biodiversity, the role of technology as a catalyst for change has never been more prominent. However, the question is no longer just about leveraging technology for progress. It is about aligning technological innovation with sustainability to ensure a harmonious balance between development and the environment. As educators, we play a pivotal role in shaping the next generation of leaders, innovators, and problem solvers. Faculty development programs like this empowers us to stay ahead in our understanding of emerging technologies and to rethink the ways in which we can integrate them into teaching, research, and community engagement. This program will focus on broad spectrum of topics, from the use of technology in monitoring environmental health, renewable energy innovations, and sustainable waste management systems, to the application of data analytics in understanding climate patterns. These technologies offer us unprecedented opportunities to address some of the most pressing environmental challenges of our time. On this note, let me welcome Dr. Anurag Gaud, Head, Department of Personality Development, NSUT, to address this gathering and talk some more about this FTP. Sir, please.
A very good morning, ladies and gentlemen. I extend heartily welcome to all of you in this 5 days faculty development program on the topic applications of technology in environmental sustainability. And I feel highly privileged and honored to welcome our Honorable Vice Chancellor, Professor Anand Srivastav sir, for having graced this occasion as a chief guest. Sir, we are very much thankful to you for accepting our request and being with us today. I also welcome Professor Yamashita from Kyoto University, Japan. He is with us on this occasion. Sir, we are also thankful to you for accepting our request to present on this occasion. I also welcome my friend and colleague at NIT Kurukshetra, Dr. Ashok Kumar from NITTR Chandigarh, providing the opportunity to conduct this FTP at NSUT Delhi with full funding support from NITTR Chandigarh. I also welcome all the respected faculty members of our institute and all the participants from various institutes for joining us on this occasion. The prime objective of this faculty development program is to educate the young researchers and teachers on this topic, application of technology in environmental sustainability. The last two words of this topic, environmental sustainability, is very, very important in the current scenario, because sustainability is important for preserving our planet and the natural resources like water and air. And it should ensure that how the humans and nature should coexist to support not only our present generations but also our future generations. We also aware that the emissions of the greenhouse gases is increasing year by year by the human activities. And because of that, there are a lot of problems. The global temperature is rising, as well as it is also disturbing the biodiversity. So therefore, it is very important we have to think seriously, critically on this topic. And you know that the CO2 emission is the most contributor in the climate change. And major CO2 emission is coming from the burning of the fossil fuels. If you look upon the data, that in 1960, the emissions of CO2, it was around 10.6 billion tons per year, but currently it is increasing now 36.6 billion tons per year, which is very alarming. So therefore, and even the atmospheric CO2 is 50% higher to the pre-industrial level. So definitely we have to get a harmonious balance between the development and the environment. So any kind of technology is only viable if it is sustainable and if it is environmental friendly. So therefore, during the 5 days deliberations of this faculty development programs, we will have a lot of discussion on this issue and what are the challenges in this area. We have very good speakers for these topics from the different institutes, from IIT Delhi, from JNU, from National Physical Laboratory, Delhi University, NSUT. So from various institutes, we are having the speakers. So you are requested to ask your doubts and discuss critically on all the points. And I hope that these 5 days deliberations on this issue will result fruitful discussions and some fruitful come out that will help to address some challenges in this area. Thank you so much.
Thank you, Dr. Gaur, for your valuable additions. NSUT is hosting this FDP in collaboration with NITTR Chandigarh. Now I'd like to welcome Dr. Ashok Kumar, our fellow coordinator from NITTR Chandigarh, to address the gathering.
So good morning, everyone. And first of all, I am thankful to NSUT for allowing us to conduct this program in collaboration to NSUT at this place. And particularly thanks to Professor Anand Srivastava, Vice Chancellor of this university, and my earlier colleague, as he already told you, and Dr. Anurag Gaur. So he helped me a lot. Then others joined, Dr. Shimita and Dr. Amit, and we are really thankful to our abroad guest today here, and he will deliver the first keynote here. And by just looking to this program and our guest, that's what we say, the harmony with the nature, as Dr. Anurag used harmony with the nature. So there's one park I remember in Japan. So their deers are together, so they can come to near to you. So they say that's the harmony with the nature. So deer park, so they will not get afraid. So you can touch them and they just roam around like this. And so one analyst from Japan also, this analysis, what he gave our roads. Normally we say our roads that we have so many animals, cows everywhere, we find accidents happens. But one analyst from Japan, I was reading, he's explaining, in India we have harmony with the nature, with the animals. They roam here and there. So this is just explanation and understanding how we explain. I will just take 1 or 2 minutes more about to tell a little bit about the institute, which is National Institute of Technical Research, Training and Research. This institute was established in 1967, and we have 4 NITRs. In abbreviation, we say NITR, NITTR. So we have 4, one is in Chennai, Bhopal, and Kolkata. We are from Chandigarh. So there are 4 NITRs, and almost they are in the 60s, 70s. Our institute is the newest one in among those. So 1967, they established 1 or 2 years ahead. Initially, the primary mandate for NITR was to give the training in the emerging areas to polytechnic teachers of both the countries, Netherlands and India. It is in the collaboration. Initially, it was established in the collaboration with Netherlands. So this was the primary job, to train the teachers of Polytechnic Institute in both the countries, that level. Later, Institute broadened its mandate, and it included engineering colleges. And today we train more teachers from engineering college in comparison to Polytechnic. They shifted. So the shifted mandate, so this current mandate includes maybe 80% engineering colleges and 20% we haven't left, because government is still, this time they communicated to us that you take the training mandate for PM3 schools also. So maybe we will also now include some of the PM3 schools as well. That's the updated, maybe for short term, not for permanent, but most of the time we take this emerging areas. This is one of the area. We take this kind of like AI areas or other areas, how to use AI in physics or different kind of topics we take. And we conduct this program to everywhere. So maybe you are not aware of the institutes or our activities. So this is not the NSUT. We private institute, we do not discriminate anybody. There are certain rules. We also conduct in private institute as well. And we allow everyone to join at our place also, Dr. Chandigarh. So if you want to come and attend the program at our place, if you belong to engineering institute, we provide all the facilities of staying, food for 5 days, everything for free of cost for attending the program. If you belong to engineering colleges, if you belong to government engineering colleges, we also reimburse your ticket for all the programs at NITR Chandigarh. So for whole 5 days. So, but this program, whatever we reimburse or facilitate, this is for faculty members. Students can join, but we do not provide any facility to students. This is like, we don't have the Chandigarh, or this is because government funding, so government is not providing that funding for students. So you can join the program, but we will provide the facility on payment basis for students. Faculty members is free for all the faculty members of engineering college at Chandigarh. So you can visit. And any other kind of questions, because I will also take some of the sessions in between. So you can ask the doubts at that duration. I don't want to take any more time. So I again thank you everyone from this institute, and best wishes for everyone. And I hope that program will be enjoyable and good learning for everyone. Thank you.
Thank you, Dr. Kumar, for giving us a detailed info about NITTTR. We will be taking up the opportunities for sure. Now, I would like to ask Professor Shigeru Yamashita from Kyoto University, Japan, to share a few words with us. So, please.
Good morning. First of all, I'd like to thank the organizers to invite me to be here. But actually, to tell the truth, I don't know this workshop until maybe 1 hour before. I just saw that I'll give my research talk here, so I'm a little bit surprised to see this workshop. For example, this kind of ceremony is very new to me. So in Japan, we don't have this kind of ceremony at the beginning of the workshop. That's very impressive for me. And I saw many temples yesterday, and I know the culture here, and I like the, staying here. So anyway, so why I'm here is that I'm doing the joint research, bilateral joint research with Professor Gupta. And so actually, with Japan considers India is a very growing rapidly and in the technology science sector. And science, and so Ministry of Science considers that we need to, collaborate with India more and more. So I think maybe I hope, and so to have the joint collaboration with Indian people. So maybe taking this opportunity, I hope to continue to the collaboration. And my research to tell you is not related to this topic, sustainability, but I'm doing quantum computation, which considered to be maybe future computing, and which is useful for the sustainable and environmental issues. So and my talk is very technical in quantum computation, so I'm not sure you enjoyed my talk. But anyway, I hope the success of this workshop. And as I mentioned that, so we consider India is a growing and maybe soon to be the powerful country in the world. So in such countries, it is very glad to see this topic, sustainability. So I hope you contribute to the world's sustainability, and also I hope this success of the workshop, and hope to collaborate, continuous collaborate with between and Japan. So thank you for your attention.
Thank you, Professor Yamashita, and thank you for being here with us today. Now, I would like to invite Honorable Vice Chancellor Professor Anand Srivastava to enlighten our audience with his thoughts.
Good morning. Good to have all of you early today in the morning, chilly morning, December morning. So Professor Yamashita from Japan. Dr. Anurag Gaur, Dr. Ashok from NITTR, Dr. Sumita Dahiya, the organizers of this event. Yashamita was speaking before me, so just want to inform that we have one MOU with Uniqlo, which is actually Unique Clothing. It's a Japanese-based company. So our students, they go for training, internship, and they also get employment. And I was told that Uniqlo has designs which is sustainable. They design clothes and they promise that this is sustainable clothing. So environmental sustainability using technology. So it's not new. We used to have environment protection law back in 70s, but nobody cared. What companies thought that this is an overhead. It is eating into their profit margin. So they never cared. At best, they thought it's a necessary evil. So this continued, even in 80s, it was not in their priority. Then there was a very exciting paper by Michael Porter in Harvard Business Review, where he mentioned that the companies which are environmental friendly or follow environmental sustainable practices are likely to succeed in future. After that, a lot of papers came, companies started thinking this direction, and now it has become very, very normal. This is a new norm in the companies, and if you want to survive, you have to have environmental sustainable management practices in your organization. See, the parameters which are used for environmental sustainability are ESG. E is environment, S is social, G is governance. So these are the metrics for using ESG. So you will not believe in the developed countries, more than 90% of the companies, they publish data regarding ESG in their annual records or in their ads or wherever. And about more than 70% people, they want to buy products from companies which are environmentally sensitive. And they like to work with those companies. And they are ready to pay more price than the average for those kind of companies. So it is gaining momentum. People are caring about the environment. So there are various benefits of having this sustainability. First is reduced cost. If you are having your system which is energy sufficient, you are not only emitting carbon dioxide, less carbon dioxide, but also your price of the product is low because your energy consumption is low. So your energy bills are very low. People, as I mentioned, want to work with those companies which are environmentally, sensitive. And if they are happy, their productivity also increases. Efficiency also increases. Suppose I have a paperless office. I don't use, papers. It is going to save environment, and also my efficiency will increase. The decisions are made over emails. Right? Let me give you a couple of examples how they follow it. For example, BMW is a car company. They now work more on hybrid and electric vehicles, so that less, CO2 emission. And also they have an environment officer, which does the advocacy of environment within that organization. And, they also source material from those companies who also care for environment. So it's a total, environmental sustainable ecosystem within BMW. IKEA is a furniture brand. They also get recycled woods for their furniture. Or they take wood from, there is something called certification, FSC certification, which is forest stewardship certified forest. So they get those woods from those places which are FSC certified. I mean, which are not no longer forest, so one can use that wood. So then 90% of the product either use recyclable wood or wood from FSC forest. So this is going to be very important, and it is not only environment sustainability. It is, there are other parameters, other attributes where one has to be very, very careful, which are actually 17 SDG goals. So climate action is one of them, which is closely related to environment, but there are 17 SDG goals, which United Nations goals, Sustainable Development Goals, which we want to achieve by 2030, and they are very, very ambitious. And ICT plays a very important role there. And when I say ICT, the underlying communication technology is 6G. And if you see 6G standards, it gives a lot of importance to energy efficiency. Earlier generation of communication was not so, not so worried about the environmental aspect, but 6G, the environmental thing is given more importance, and they want to design systems which is 10 times more energy efficient as compared to present day systems. Because 6G is going to be the underlying technology which is going to help all these SDG goals, whether it is poverty, hunger, education, or life below water, life on the land. There are various SDG goals. So they all use ICT, and it is proven that ICT based on 6G technology is going to achieve these highly ambitious SDG goals by 2030. So in all, the focus is to have net zero. I mean, whatever you spend, you should be able to conserve somewhere. So the goal is to have net zero energy emission. And in US, for example, you have, greenhouse emission gas. There's a target that you should decrease to a level half of the 2005 level by 2030. So all the big companies, the Googles, the Amazons, the Apples, they have committed to this. And they are using sustainable practices within their organization so that they are able to achieve these goals. So with these words, I welcome all the participants who have come here. And I also thank the organizers for organizing such a good event. And I'm thankful to NITTR for supporting this event and giving various lectures and discussions. And I hope the participant will gain a lot of valuable insights, how to use technology for environment sustainability, and they'll be using this in their day-to-day practice. Thank you very much.
Thank you, sir, for giving us this insight. Your words always motivate the academic community to do better and to keep challenging ourselves in these changing scenarios. I'm confident that these sessions ahead will provide a platform to exchange ideas, foster collaborations, and inspire actionable insights. I encourage each of you to actively participate, ask questions, and think critically about how we can collectively contribute to a sustainable and equitable future. The organizing committee had made genius efforts in bringing together such an impressive lineup of speakers and sessions. I'm sure their vision and hard work will make this program an enriching experience for all of us. Now, technology gives us the tools to reshape the world, but sustainability reminds us of our duty to preserve it. The intersection of these two ideas is where true progress lies. With this concluding remark, I once again welcome you all to this faculty development program. Now let's meet up at 11:30 for our first session with Professor Shigeru Yamashita, Kyoto University, Japan. And now, finally, it's time for the tea. So I welcome you all to have tea. Thank you.
Good morning, participants and team. Now we are going to start our sessions. Our first session is related to quantum circuit design, which is going to be delivered by Professor Shigeru Yamashita. Shigeru Yamashita is a professor of College of Information Science and Engineering in Ritsumeikan University. He received his BE, ME, and PhD degrees in Information Science from Kyoto University, Kyoto, Japan in 1993, 95, and 2001. In 1995, he joined NTT Communication Science Laboratories, where he engaged in research of computer-aided design of digital systems and new type of computer architectures. During 2000 to 2003, he was also a researcher at Quantum Computation and Information at IRATO under Japan Science and Technology Corporation. During 2003 to 2009, he was an associate professor of Graduate Science of Information Science, Nara Institute of Science and Technology. He also served as visiting professor at National Institute of Informatics from 2012 to 2017. He received the 2000 IEEE Circuits and Systems Society Transactions on Computer-Aided Design of Integrated Circuits and Systems Best Paper Award, SASMI 2010 Best Paper Award, 2010 IPSJ Yamashita SIG Research Award, SASMI 2018 Outstanding Paper Award, SASMI 2018 Outstanding Paper Award, Meribon Academic Achievement Award of the Meribon Research Promotion Foundation, and many more in the list. He is a senior member of IEEE and IEICE and a member of ACM and IPSJ. I would like to call upon Professor Yamashita on stage for his expert talk on quantum circuit design. Welcome, Professor.
Thank you very much for the kind introduction, Professor Gupta. So as I mentioned in the previous session, so this talk is not related directly to the sustainable issues, but I'd like to introduce my research topic. But before that, I introduce some basic of quantum circuit. Okay. So probably my topic will be less than 1 hour, so I can take any question concerning Japan or quantum computation in general, so after my talk. So please bear some technical, little bit non-interesting technical stories. But anyway, let me start. So probably, so I came from Japan, so I'm not sure you know Japan. So this area is called West Side. Actually, in the past, this is a historical center of Japan, but now you know that Tokyo is the capital. And I live in Kyoto, and our university, Ritsumeikan University, has 3 campuses, and this is a brand new building from this April. And our department actually is the largest department for information science in Japan. We have more than 2,000, probably 3,000 students, and more than 100 faculties for only information science department. And also, our department is very strong in the sense that in the ranking of the research funding in Japan, our area, our department would be first or second. And then, so, okay. So if you're interested in these related cultures, please ask me before, after the session, or maybe during the session after my technical talk. So, although, Anka already introduced me a lot, so probably this is my background, and my background is actually computer science, and especially mainly for algorithm and data structure for logic synthesis. And at first of my career, I did pure logic synthesis for conventional computer circuits like field programmer gate arrays. Sorry. Doesn't work. So let me see. What? Okay. Okay, so as Ankara mentioned, so I belong to the national laboratory called NTT, which is a telephone company, and do some basic research for communication and computers. But unfortunately, the group I belong to is terminated, so I forced to change my topic. And at that time, luckily, there is start called ELAT project. This is a national, a very big project. And then at the year 2000, that project starts for quantum computation. And so as a researcher of this project, I start my research for quantum computation. And since that, I mainly do the quantum circuit design so far. And I moved to universities, and now I also do some research for biochip design. And so as I mentioned, I do the bilateral research collaboration with Professor Gupta for this biochip design. And also, actually, so there is a big, very competitive and big grant in Japan for quantum computation, and I successfully got this funding. So anyway, so this is my introduction. Okay, so let me move to quantum circuit. Before that, so let me introduce this moonshot program, which is a governmental program. So as you know, moonshot is a kind of very ambitious to get to moon. So the government, Japanese government, want to set some ambitious goals, actually 10 goals here, which should be due until 2050. And one of them, see, maybe this is very small, but so please Google moonshot if you are interested. So for example, there is some topics for AI or topics for environmental or sustainability, of course. So, and disease or health, something like that. And one of 10 topics, this goal 6 is concerning for quantum computation. And so, like other countries, so Japan considers quantum computation should be the future technologies. Of course, sustainability is one of that. And this is a moonshot project. And actually, so I'm a sub-program director of this whole project, and we have these 7 people for conducting for device level. And you may not know, but for the device realization for quantum computation, Japan has a leading researcher like them for photon or superconducting. Actually, superconducting, Japanese researcher first realized this. This is now, you may know that IBM doing commercial quantum computation based on superconducting. And so there are many possible candidates for quantum computation, and I should say that trapped ion is Japan is a little bit behind, but other devices, I think Japan is leading the top of the world. And for the system side or computer science side, so actually theory for quantum computation is also advanced in Japan. So for this project, actually, this has approximately 10 billion rupees per year for this project. And this is a 10 years project until 2030. Okay, so I'm not sure your knowledge for the quantum computation, but let me start very rough image of quantum computation. First, quantum computation uses quantum bits, which is correspondence of the classical bit 0 and 1. And we use very tiny quantum states like electron spins, and there is 2 distinguishable physical states, 2 level states, and we call one is 0 and one is 1. This special notation is bracket notation, just represents the quantum states. So maybe you can consider this is 0 and 1 in my talk. But unlike the classical states, 0 and 1, these quantum states can be superposed like this. some complex coefficient 0 plus some coefficient 1. This is one state of the spin. And so this is kind of a superposition of 0 and 1. And actually, this stores superposed information, which is the main reason for the quantum computation to be powerful. But in my talk, actually, the content is almost classical, so maybe you can forget this. And the quantum circuit is a computation model of the quantum computation. And for the future quantum realization of quantum computation, we do need the circuit methodology for this. And so there is a research area for designing quantum circuit, and I'm working on it. And I introduce my recent topic in that area. So probably it is a little bit technical, but I just want to introduce that. And in the quantum circuit, so here, this one line is related to one quantum bit, like electron spin. So here we have 3 quantum bits. And the time goes from left to right, like this. And this kind of diagram related to some operation, which called quantum gate. But actually, this is not the hardware, but this is some, for example, pulse. So this is a software operation. This is called Adamar gate. Adamar gate becomes, so here X is 0 or 1. So for example, if we input 0 to Adamar gate, then this operate to output like this. So this is a coefficient, what we call phase. And in my talk, actually, I would like to say that for the computation, it is important to realize classical Boolean function. And to calculate classical Boolean function, these two are logically based components. This is called Toffoli gates, which is proven to be classical computationally universal. So if we have this Toffoli gate, then we can calculate all the classical functions. So this works like this. So these two are called control bits, and if both of them are ones, then we invert this target. This is called a target bit. So this means that if the input is 1, 1, 0, so 1, 1, 0 from left to right, then this input changed to 1, 1, 1 because these two inputs are ones, so we invert this. So if the input is 1, 1, 1, then the result is this. Any questions so far? So if we can write this functionality like this, x, 1, y, z is either 0 or 1, so Boolean values. So this is exclusive OR. So if they are ones, then z is inverted. And so in the quantum circuit design, this Toffoli gate is key to design logic functions. And this is C0. This is just one control bit. And Toffoli gate, actually, we cannot implement directly physically. So this is have to decompose to more physically easier gates, and C0 and some T gates. Dagger is just reverse operations, but almost similar to T gate. And here, Adamar gate, this is H gate and NOT gate. And in the future quantum computation, we consider that we need to do some error corrections because quantum computation is not perfect. And if we use error correction, then we need some error correcting code in which these logical gates has thousands of operations. And to implement a T gate in the error correction nodes, actually the cost is very huge. And NOT and H gate can be done very easily. So in the quantum circuit design, we consider that only T count is very important. In this case, for example, Toffoli gate has 7 T gates. and not gate is, so the cost of this almost negligible. So this is one point. As this is a very important point in the designing of quantum circuit. Okay, so maybe, okay, so let me continue. So as you may know that there is two famous algorithms in the quantum computation originally. That is Shor's factoring algorithm, and another is Grover's search algorithm. So you may know that Grover is Indian guy, and this is a circuit for Grover iterations. So here we have some Boolean function which is related to a problem. And this is some special part for what we call so inversion by the average. So this is some quantum specific operations. But it is interesting that, for example, if we use global search, then this quantum specific part doesn't change for specific problems. But for specific problems, we need to design only this part, functional part. So, as I mentioned, to design Boolean function is very important in the quantum computation domain. And this is a formal model of quantum Boolean circuit. Quantum Boolean circuit is a quantum circuit which calculates Boolean function. And so here we want to implement n variable function like this. And so these are inputs, x1 to xn. They are inputs. And this is a special bit where we calculate the answer like this form. So this is exclusive. And we may have some internal auxiliary qubits which can store the intermediate results. But interestingly, so maybe it is important to reset to these values, to the initial values, because if not, this cannot be used in the quantum algorithm. Because maybe I cannot explain, but in the quantum algorithm, we need to interfere with quantum states. So if we use this kind of quantum Boolean circuit as a sub-circuit in the whole quantum algorithm, then these inputs should be reset to the initial values. So this is a model of quantum Boolean circuit, and our task is the number of topology gates is minimized to realize some target function. That is the main goal of our research community. And there are a bunch of researches, but so I explain 3 topics. Maybe it is a very technical thing, so I'm not sure. But so far, any questions so far? I'm not sure your knowledge, so any question? One more thing, actually, so this is not related to sustainability, as I mentioned, but the one most promising application which is considered now for the quantum computation is to calculate chemical energies, which is useful to design automatic photosynthesis. So if the quantum computation fault-tolerant large quantum computation is realized, then it is considered that it can be used to be useful for the photosynthesis, which means very sustainable results. So in some sense, this talk is related to sustainability in the future. So anyway, any questions so far? Okay, so, okay, please.
I have the question, maybe not maybe right time right now, maybe I was thinking to ask later, but I'm just introducing the question, maybe you can keep in mind and introduce it later as an answer. So like the second law of thermodynamics, we know that entropy is universe is consistently increasing. So if
Entropy.
we can reverse, if we can go back to any ordered system like crystal, so the entropy is less, means more ordered system. So 2-3 months ago, scientists, they, by the calculations using the quantum computing, they achieve the previous state of the crystal. So that means they are going back in the time. They claiming that because that is the more ordered state of the crystal. In future, the next step is going to the higher disordered. So previous state they achieved by using the quantum computing. I'm not sure how they achieved, how they proved.
Oh, sorry, I'm not sure about that. Oh,
The second law of thermodynamics. So that says the entropy of the universe is consistently increasing. That means the future states, they are always more disordered than the current state. So if somehow we can achieve the less ordered state, that means that is the back in time. So,
okay, probably yes.
with quantum computing, 3 months ago, Russian scientists proved with quantum computing the crystal which is now, they can go that previous state, that means less disordered state, more crystalline state than the existing one. So that means they are going back in that time.
Really?
So that they, by using quantum computing, they proved it. So I just want to know any logic or any simple way to understand how they did it all.
I think because I'm not a physicist, yeah, that's very difficult question for me. I don't understand. Sorry, I cannot answer. But yeah, that's very interesting story. I'm not sure. Sorry. Oh, really? Okay.
Okay, thank you.
Yeah, thank you. But I cannot. Okay, so I should proceed. So the first topic, maybe this is very technical, but at first it is we considered how to decompose the inputs. So in the logical level, for example, if we want to calculate 1, 2, 3, 4, and actually this calculate 4 input AND gate. This is 4 input. So meaning that if, so this is negative control and this is positive control. So if I say this is x1, 2, 3, 4, then this is inverted when this is 1 and this is 0 and this is 1 and this is 0. So this kind of gate is logically important and what we call mixed polarity multiple control Toffoli gate. And then, of course, this is not physically realizable, so we need to decompose this. And there are many decomposition methods proposed. So maybe I'll skip this. So for example, this is one decomposition way. So if we are many inputs, then this is decomposed to a series of Toffoli gates. So this is an intermediate. So for example, this is the end of these two or something like that. So we can decompose this like this. So this is and also there are other decomposition methods. And so because they use some auxiliary qubits, so the optimization method considers to decrease these numbers. So there are some research. So there are many ways of decomposition. So this is one topic in this community, but okay, so. And another topic is how to treat large functions. So probably we want to decompose, we want to realize more than 100 variables functions in the future. And it is proposed by using LUT. LUT is a lookup table for the conventional computer architectures. So that is, so this is conventional logic synthesis, so already established. So there is a logic synthesis method. From the large function, we decompose these to some, for example, these are maybe 2 inputs and 2 inputs or something. So we can make this kind of tree of and ors. Then we group some subgraph. For example, in this case, this is one graph. So here, and this this portion would be this. So the idea is that, so if, for example, in this case, if we group these as a 3 input, then this subgraph is a kind of a sum function which realizes 3 input functions. And this can be mapped to LUTs. And conventional FPGAs has nowadays 4 to 6 input LUTs. So first, there is a bunch of design method for 4 LUT or 6 LUT network synthesis like this. Then, borrowing this result, so we can convert this to quantum Boolean circuit very easily. So and I think, so this is proposed in 2019, and this probably is the only practical and scalable method to designing a large quantum Boolean circuit. So here, for example, this is 1 LUT, 3 inputs. So we realize here 3 inputs function to here, for example. So this is some realization of three inputs or 4 inputs. And for small inputs, maybe we can design quantum circuits. So we design these sub-circuits. And for example, this is 3. 3 needs the output of 1. So this output is used here. So something like that. So from this, we can create this. But here there is an optimization problem that to decrease these intermediate qubits, which is discussed in this paper. So anyway, so my message here is that for the future large quantum computation, we already have a design methodology to realize large Boolean circuits. So maybe. Okay, so now let me introduce my recent research. This is a little bit very technically. So again, so let me show these famous decompositions. So Toffoli gates has 7 T gates. But interestingly, there is another Toffoli gate, which we call relative phase Toffoli gates. So this is this diagram is a little bit different. And here we have only 4 T gates. So this is much less physical realization cost. But this doesn't work perfectly as Toffoli gate. So we call this as relative phase. So maybe this is a messy part now starts. So here, this is truth table, but it's okay. So for example, this is an input, 0, 0, 0 means here 0, 0, 0. And if we got this input, then the output is 0, 0, 0. So this corresponds to 1 from left to right. So we have 3 inputs, which means we have 8 patterns of inputs. For example, if we have 1, 1, 1 here, 1, 1, 1, then our output becomes 1, 1, 0. So as I mentioned, Toffoli gate inverts the third bit if both of 2 are 1s, okay? And for example, if this is 1, 1, 0, then output becomes 1, 1, 1. So because these 2 are 1s, so we invert this. So if we look these states, it works as Toffoli gates. But why we call this relative phase? Because there is some phase is on the result. What does this mean that, maybe this, okay. So this is 1, 1, 0, okay. So, okay, for example, if the input is 1, 1, 0, here, 1, 1, 0, then the output becomes this. So this is phase information. So the correct Toffoli gate, there is no phase added. But these Toffoli gates are using less T gates, but add some redundant, unnecessary phase information here. So this table shows that if the input is 110, then the output is 111, but additional phase, something like this. So here we had 3 additional phase. For example, if the input is 101, then there is additional phase pi here. And in the quantum computation, actually, input can be superposed. For example, we can fit these 2 states superposed. So this is maybe origin of the power of quantum computation. So in the classically, we need 2 times to compute this case and this case. But in the quantum computer, if we fit these superposed states, then just one operation of these gates, we get this output as a superposed states. So this is called quantum parallelism. And anyway, so this gate is a little bit messy, but it is proposed that how to use this relative phase Toffoli gates. So as I mentioned, this is a decomposition of Toffoli gates. Many input Toffoli gates. For example, this is one. But here, interestingly, there is a same Toffoli gates, corresponding Toffoli gates. So if we replace these Toffoli gates with relative phase Toffoli gates and replace this to the dagger. So dagger means in the quantum computation, actually, so this is one circuit. And if I put these operations in the reverse order, then the operation becomes daggers because these metrics are self-inversed. So it is easy to implement the dagger inverse operations. So if we implement this as RTOF and this as RTOF dagger, then the added phase information is totally canceled here. But the function is actually calculated as a Toffoli gate. So these, you see, there are many correspondence Toffoli gates. So they can be realized by only RTOF. So this is proposed to use RTOF. So I'm sure you are following me, but it's very difficult. So if you have any question, so. Yes. These means, what are you mean these?
Means like we have to measure the polarization state of the entangled particles or strings. Can you tell us, even in the quantum computing, what are the components, are the major components of the quantum computers other than the classical computers?
You mean what are the basic components for these?
Memory, how the calculations being done.
So for example, for the superconducted qubits, so we add some pulse to them. And depending on the time duration of the pulse, we can control the rotation angle for the quantum states. So for example, for this H operation, we have some specific pulse durations. And so the controller can emit the pulse to operate on this. Is this answer to you? So we have specific pulse length and also frequency to the qubits. Now for these interactions, this is a little bit difficult, but still there is some resonance frequency which correlate these two bits. So yeah, to add some energy or to add some pulse, we can control quantum states.
Means there are certain crystals and they will do this.
Excuse me.
There are certain crystals, they are doing these calculations. We don't have some different kind of the gates and all the ICs, they are specially made for the quantum computers.
Yeah. But because I'm working on the okay.
What would be the effect of these phase that we are getting in our output?
Good question. Actually, for example, what we want to do is implement quantum Boolean circuit. Sorry. So we want to realize this circuit model. So here we have quantum inputs and outputs like this. And here there is no added phase, okay? If there is an added phase, so actually just compute this value, phase does nothing. If we measure this result, we can get the answers. But as I mentioned, this is used as a subroutine in the, for example, global search or as quantum specific algorithm. Then, if there is some added phase here, in the subsequent computation, there is no what we call quantum interference. So by using such quantum interference, we got the quantum algorithm. So if there is some added phase here, this circuit cannot work as a subroutine in the quantum algorithm. So we need to cancel this phase anyway. Please.
I want to know if someone has to start working in this direction, what is the starting point and the prerequisites? As a starting point, if one wants to go in this direction, wants to do research in this direction, from where should they start?
Okay, so this research maybe, okay, let me. Sorry. どこや? Maybe it's very difficult. I'm just, where is it? Okay, for example, this is a whole quantum algorithm, for example. This is famous for as global search. In such a quantum algorithm, so there is a part to calculate Boolean functions, which is specific to problem instance. And other part is quantum specific operations, which is the same for the problem. So if we want to do quantum search, for example, this part doesn't change, and this part should be changed. For example, if we want to solve SAT, satisfier problem, from the functions, from the Boolean functions, then we need to design a Boolean function, a circuit to calculate the Boolean function which relate to the SAT problem. So this part should be very important to design. And this is a model. So this is the input, and this is the target function which is given to us. And our task is to design this as few as possible. The cost should be, realization cost should be the lowest as possible. And the cost is counted by the T gates. So these Toffoli gates consists of 70 gates. So we want to somehow, we want to decrease the number of topology gates. And there are many methods proposed. And there is a benchmark circuit, and we compete with the result for the benchmark circuit, how many topology gates are needed to implement the given benchmark circuit. And also, and here, so as I mentioned, so this quantum Boolean circuit is used to be, for example, if there is some additional phase here, then this part actually utilize some quantum interference effect. But we cannot, how to say, the algorithms work to use the quantum interference if there is some added phase. So this part strictly calculates the Boolean function with this model. So input should be restored to the original, and also auxiliary qubits should be restored to the original. Original means there is no added phases. I'm sure, see, it is
We
answer.
are getting additional phases with this relative phase topology Boolean circuit. Will it increase the errors?
Sorry, but what do you mean? If there is a added phase?
In Boolean circuit designing with relative phase topology gates, we were getting additional phases like pi by 2 phase.
Excuse me, what do you mean?
I think his question is the phase difference, whatever we are getting, that will remain same, or this will be pi by 2 plus 0, 0, 1, something like, or error, or it will be exact pi by 2 always. The difference, phase difference will remain same, or it can also vary. It can have some kind of error also. Minor error.
Final error?
Minor error in the phase difference. So you are showing some phase difference pi by 2 pi.
Pi.
It will be always same, or is the question it will have plus minus something.
Plus minus something,
Theta.
yeah.
It will have or not?
Sorry, excuse me. Understand.
For the quantum interference, so there will be some phase difference between the two quantum waves.
So there is a phase difference in the output. So when you so like you have 0 phase difference, pi phase difference, pi by 2 or 3 pi by 4, something like. So this phase difference according to input will remain always same, or it can also have some kind of error, right? Phase difference plus minus theta. It can also have some theta kind of error, or theta is always 0.
Theta?
There is no theta. Some
No,
angle.
no theta. So where is it?
Next. Yes. This one, please. Yeah. This one, yeah.
Yeah.
The phase.
So
This
this,
will always remain pi by 2, or it can have slight variation in this value.
yes. But what's the question? So yeah, this happens here.
Okay, we got it.
So so they are little bit different. Most cases it's 0, but sometimes.
We got it, thank you.
Yeah, if they are all the same, then that is called global phase. Then global phase doesn't matter. Global phase doesn't matter, but relative phase like this does matter. This is very bad for the subsequent quantum interference. Okay, so far. So, okay, I'm sure. So now let me introduce our research. So our research is how to utilize this RTOF other than such a decomposition. Okay, so this is again. So this is RTOF. So the cost is small, but there is some unnecessary phase added. And actually our proposed method is very easy. That is, we are given already synthesized Toffoli gate networks. Then we just replace all Toffoli gates with RTOF gates. And of course, then there are a lot of added unnecessary phases. So our strategy is cancel this. So, okay, so let me, okay. And here, actually phase is the multiple of pi over 2. And of course, if the phase becomes 2 pi, then that becomes 0. So there is 4 cases added phase is only 0 or pi over, so multiple of pi over 2 until 2 pi. So let's say, we just say this is 0 and this is 1, 2, 3 for simplicity in the following. So for example, this is already designed circuit and how to use RTOF here. So as I mentioned, for example, in the top level here, these 3 are inputs. And this is a target bit where we calculate function f. So as I mentioned, these 3 values should be restored. For example, to restore this, for example, here this is G1 and this is G1 dash. So this is so cancel. So we get the original values. So this means that for the upper part, we always have the correspondent gate to cancel. So it is easily, for example, for this G2, we have Z2 prime here. So it is okay to just replace RTO, this is RTOF and RTOF dagger. But for these gates, actually this is contribute to calculate F. Then this doesn't have a, in this case, this seems they are same. Sometimes there is a, how to say, okay, let me explain that. This gate and this gate seems the same, but here actually the input is different, so they are not exactly the same. So in these red gates, we cannot simply replace with RTOF. If we replace these gates with RTOF, then there is some added phases. So, okay, our method is to calculate added phases anyway, and then try to cancel them. That's a very simple idea, but so this is a little bit messy, but I try to explain this. For example, we have 3 inputs here. So here we have 8 combination of inputs, 0, 0, 0 to 1, 1, 1. So we have 8 possible patterns. And the fourth bit is just input 0. And for example, if this is input 0, 0, 0, 0, then after gate G1, 0, 0, 0, 0. So we can see something like this. So for example, after gate Z4, okay, go back. So after gate G4, so if this is RTOF, then a little bit difficult. So there is some added noise. For example, let's see the fourth column here. So before this gate, fourth column is the 3 inputs for the Toffoli gate, x2, x3, 0 is 110. So here 110. So becomes 111 because these two inputs are ones and this is 0, so inverted 111. And if this is RTO gates, in this case there is added pi over 2. So something like that. So we can continue this calculation until the end of circuit. And this logical function is perfectly same as a Toffoli gate case, but there is some added noise here. So this is written as 033, something like this. This is a vectors. For eight input patterns, we have this. And interestingly, so there is some special gate. Okay, so S gate and T gate. So this is, we consider we can use this. So this is T gate. As I mentioned, this is very expensive. And this is S gate. This is not expensive. This is actually primitive in the error corrected form. So this is almost nothing. So here, this is a little similar. But this means that if x equals 0, then here 0, which means if 0 comes, then output 0. And if 1 comes, then output this added phase. And here S gate is also. So this means that if we put S gates at where the logical value is 1, then we can add this phase. So this is our idea. So, okay, in this case, what happens? Here, this is unnecessary added phase, but actually here, this is the output function. So this means that, so for this input 0, 0, 0, the last bit becomes 0. So these 8 patterns, and for example, this is 1, 1, 1, then output becomes 1. So these vectors can be considered as a truth vector for the final output. So that is, which is realized here, final output here. And if we put S gate here, what happens? So as I mentioned, if we put S gate, when the value is 1, then this add this phase. So this is the function at the last. So if we put S gate here, then this S gate add the second input pattern, third input pattern to add pi over 2. So, okay. So, okay, let me summarize this case. That is the output function, the vector is this. And if we put S gate here, we can add the phase here, so 0, we can add this phase here. And that last phase, first added phase here, so if we add this phase to this, then we get this. This means that we can cancel these. So because 4 becomes 0 again. So our idea is that we try to find the function which cancel these phases in the circuit and just put S gate to cancel this like this way. And of course, there may be some part which cannot be cancelled. So to deal with such cases, so we just add. Let me explain again. So this is only 4 vector cases, and this is, suppose this is added phases. And then, for example, if there is a function, something like this, then if we put S here, then we add 1, 1, 1 here. And if there is this function somewhere, then if we put the S gate here, then we add 1, 1 here, and something like this. So by adding 3 S gates, here we can add 1 phase and 2 phase and 3 phase, so totally cancel all the phase, something like that. And of course, there still remains some phase which cannot be cancelled. For such cases, okay, so in such cases, for example, this part, so we make this function 0, 0, 0, 0, 1, 0. So in this case, this function is just this. So we make this function at the beginning of the circuit and apply S gate and cancel, and then added that part. Then this part adds the added phases which can be cancelled with this added phase. So this is whole procedures, so which is recently presented at the ICCAD. So, okay, maybe this is very, but in this case, so in this specific cases, so original case we have 14 Toffoli gates. So that T count, so as I mentioned, each Toffoli gate has 7 T gates. So T count, which is actually our target cost criteria, is 98 original in the original circuit. And as I mentioned, a conventional way, so we replace the Toffoli gate with RTOF if there is 2 correspondence gates. So in this example, there is such a Toffoli gate, 6 Toffoli gates. 8 Toffoli gates can be replaced with Toffoli gates, and 6 Toffoli gates cannot. So this is a conventional method, and our method can replace all the Toffoli gates. So all the Toffoli 14 gates can be replaced with RTOF, so which is a T cost here. And as I mentioned, so there is some remaining added phase which cannot be cancelled. So to cancel the such phases, we add some additional logic. But in this case, still the cost is decreased. So this is our proposed method. And so this is for some benchmarks. So it's messy, but I should say that in some cases, our method can decrease the cost. But in some cases, because there is many remaining added phases, our method cannot decrease the cost. So maybe this is my technical part. So okay, so this is the end of my talk. So if you have any question, please let me know. Thank you.
For cancelling the extra phase, we are using S gates. Will it increase the cost? Like in big Boolean circuits, we have to use many S gates then.
So you mean using the S gate?
Will it increase the cost of the circuit?
So actually S gate should have some cost, but which is very small compared to T gates. And currently we consider that we only focus on the number of T gates, which is called T cost. So in this community, we are always compete with the T cost. But in the reality, of course, the cost of S gate is not 0. So we should consider, but at this moment, we don't consider.
So the basic purpose of this research is to decrease the cost or to increase the efficiency of the computing. So what is the basic purpose of this research?
Essential computation.
Efficiency?
T gate is, so to realize T gate, we need a lot of time. So if we can decrease the T count, then the computation time for the total computation should be decreased. So which means maybe efficiency. But also, maybe we can decrease the number of physical qubits. So maybe we can decrease the cost as well. Thank you. should be very technical one. So.
Professor, you can sit. A very insightful session, I must say. On behalf of NSUT and NITRR, I extend my heartfelt gratitude to our esteemed guest speaker, Professor Shigeru Yamashita, for sharing his profound knowledge and insights. Professor Yamashita, your groundbreaking research and innovative strategies have not only deepened our understanding of this critical field, but have also inspired us to think beyond conventional approaches. We are truly honored to have had the opportunity to learn from your expertise. Thank you so much. Next, we will meet at 2 p.m. for the session with Professor R.S. Dhaka, IT Delhi. Lunch will be served shortly. Please collect coupons for lunch from the registration desk. Thank you. Our next sessions will be conducted in APJ 5.